Yeah, good morning. So today I would like to do two things. I would like to show you what is the structure of hard thermal loops if you have gauge theories. And the other thing is how these are related to something seemingly completely different, which is classical plasma physics. Okay, so last time I argued that if you want to compute the production rate of axions in a hot system like early universe, you should compute these type of diagrams, 2-point functions of this FF dual. And the first non-vanishing contribution you get from this two-loop diagram here. When you do the loop integration, then you encounter a problem because this loop momentum here can become soft, which then gives rise to an infrared divergence. Now we've seen in the scalar field theory how we can fix that by resumming these so-called hard thermal loops, like putting many of these blobs here with on this line, so that so this line is soft, has low momentum, much less than the temperature, and then these inside these blobs are the typical momentums order of the temperature. That's why they're called hard thermal loops. And if you do that, then this propagator is screened at small momenta, and then your integral is finite, and you get some finite result for the production rate, for the in the case that we looked at the pressure. Now, okay, to do this, we need, of course, what is the hard thermal loop here? So we so hard thermal loop meaning the gauge field hard thermal loop gauge field, because this is it. This is the field into which this is resummed. Hard thermal loop in. And for simplicity, I consider electrodynamics, quantum electrodynamics. So these type of diagrams that you have to insert there, they give you this polarization tensor, pi mu nu, of k, which you know from principle also from zero temperature field theory. In imaginary time formalism, this is the Fourier transform of a two-point function of electromagnetic currents. So let's write it like this: k dot x, and then you have j mu of x, j nu of 0. Which is represented by this type of diagram here. So what we want to do is now we want to look at this polarization tensor in the hard thermal loop approximation. So we consider a momentum k, which is soft, and then in the momentum carried by the current, by the particles which give you the current, these are hard. So in terms of Feynman diagrams, we can write this as, well, like this again, where now this is k, and let's call this here p, and this is then p plus k. Okay, so let's do the write down the propagator. So we are at very high temperatures, then neglect the fermion mass. So we have here massless propagators. And so with the propagator is 1 over, say, p slash, which is p slash over p squared. So we have Dirac matrices in the numerator, where we take the trace here. I won't write this explicitly, but just the terms that we need. So we have two vertices, two coupling squared. Then we have the Matsubara sum for the P naught, which is fermionic, as I explained yesterday. So it's an odd integer times pi t. Then we have this stuff from the trace upstairs, which is a function of the momenta here, and in particular it's also a function of the P naught that we sum over. And in the numerator then we have 1 p squared from this propagator, and then p plus k squared from the other propagator. So here you have poles from this thing downstairs, and here upstairs there are no poles. So this is why we don't have to specify this so well. And of course we also integrate here over the spatial momentum p. Yeah, eventually we want this to be, that's the difference compared to the scalar field, to the computation of the pressure. We now need this here at real frequencies. Or to be more precise, we need the limit of going to the real axis from above and from below. This we cannot use here so far. In this expression, we can only use it after we do the Matsubara sum. So let's first do the sum over Matsubara frequencies. This works like very similar to the case where we had bosons. So this is the complex P naught plane. And now the poles are not at 0 and then 2 pi t and so on, but they're shifted by pi over t. So they're here. And then we can deform our contour, which was originally around these poles, to look like this. Okay, now the goal is to move this to plus and minus infinity. And if we do that, then we hit the poles of here, this expression. We have, where are they? So we have a pole at here and here, from where the p squared vanishes. This is like at EP and minus EP. EP in this case, this is the one particle energy for momentum p. So in the massless case, EP is simply the length of p. That picture we had before. In the scalar case, we have 2 poles. But now we also have a second denominator here, which gives us 2 more poles. And for now, the frequency in the k here is still imaginary. So the other poles are, well, shifted in this direction, but they also shifted into the complex plane. So maybe they could be here. So this pole would be at, maybe draw like this, at minus k naught, and then plus e p plus k. Yeah, this is one of the poles of due to this denominator, and the other one is then at here plus minus k naught minus e p plus k. Yeah, so when we now move this branch of the contour, we hit 2 poles, and same here. So we get 4 poles. So the computation is more involved, and so this here becomes then looks like this. We have one contribution from this pole here, one from this pole, one from this pole, and one from this pole. Okay. So I don't want to do all of them because that involves a lot of writing. So let's just consider one pole here and see what we get from that. Okay. The pole at P naught equals to EP gives following expression, what do we have? We have the e squared, and then this here became the integral, and that has a positive, no, negative. I mean, this goes clockwise. This gives us a minus sign, and so we have minus e squared, and then the integral over over the momentum. And from this contour trick, we have the minus 1/2, the Fermi distribution, evaluate, and now this was at omega. Now we pick the pole at EP, so it's omega at EP. From this propagator has the residue 1/2 EP. So we have 1/2 EP downstairs, and upstairs I have the T mu nu, where the P naught is also replaced by EP. And now comes the most interesting part, which is, I mean, this looks all kind of similar to the scalar case. The big difference comes from the second denominator. So what happens with that? Let me just write it now here the same way as there. So it's P plus K squared, where the P naught is equal to EP, meaning that P squared is 0. So this momentum here is on shell. So P is on shell. So that P plus K squared equals to, P squared is 0, so then we have 2P dot K plus K squared. Yeah, so we see that this is not simply a constant here or something which is independent of the momentum k. So we get some k dependence into this integral. And now we can still simplify this, because remember we consider soft k, meaning it's much smaller than the temperature. The integral here, we cannot quite see it because I didn't write explicitly what the T mu nu is, but the integral is again saturated by hard momenta. So the P integral hard momenta, remember, that means that P is of order T. So that if you now look at this expression, you see that here the first term is, this is hard, this is soft, so this is has 1 power of a soft momentum, whereas this is soft squared. So then we can neglect the second term. Yeah? Then, so this whole expression was P dot K squared, and this is now approximately to P dot K, which we can write out. So it's P2 P naught K naught minus P spatial dot K spatial. The P naught, we said, is the one particle energy EP, which is also the length of this vector. So we can write this as, so we can pull out the energy EP and have left here k naught minus the unit vector in p direction, which I call v. V because it's the velocity of a particle with this momentum. So this is v is unit vector in p direction. So this it's the 4 vector. No, the 4 vector is a unit vector, is p squared equal to 0. But this is the spatial part. This is just the 3 momentum.
You've taken an E mu out. Sorry. You've taken an E mu out already, right? So there should be no more magnitude left over because vector p and p naught must have the same magnitude, right? If p squared is 0.
This is two. This here is two. This is clear, right? This is p dot k. This is this here.
Huh? Oh, he's the. Okay, thanks.
Okay, but then so what we see now is that this kind of new. This is really the new thing here today. This is this expression. This expression factorizes into this length of the vector p, and then something which only depends on the direction. And if you look at the rest of the integral here, we also only have the energy or the length of the vector p, same here. This thing I don't show you because it's a bit long, but there you can also separate the energy and the direction of the p, so that the whole integral here factorizes. So we have integral d3p, that is integral from 0 to infinity dp length of p times p squared, and then integral over the direction, and the integral is over p and omega factorize. Now the integral over p gives us, well, just some that we can do. I mean, the only non-trivial there's only dependence on energy, so we have an integral of the type, we integrate over the energy here, and then we have the Fermi-Dirac distribution and only energy and only this dependence on p squared, and this integral we can do. And this gives us something proportional to t squared. Okay, sorry, I forgot to say one thing. I mean, here is, when I did this argument here, I have done the analytic continuation already, right? Because I had originally, before I did the sum, I had to take the k naught to be in Matsubara frequency, but after this step of doing the contour integration here, I can do the analytic continuation. So I should say at this point we make this step. Continue the k naught. Because otherwise this statement wouldn't make sense for the frequency. I mean, the fermionic frequencies are never 0, they are always of order t. So to make this kind of statement, we have to, with this we can make only after the analytic continuation. Okay, But then the integral over this here becomes simple, and we can do it, and then we are left with an integral over omega. And now you have to do, you have to collect all these terms, compute all these traces here, and I just show you what is the final result. So adding, so the p integration can be performed, and they give something proportional some number times t squared, as we did in the scalar case. So this is the hard thermal loop, the typical hard thermal loop contribution, and then adding all contributions gives now the final formula for the hard thermal loop. Pi mu of k is thermal mass, which in this case is called the Debye mass. It's 1/3, and then in principle, if you have several flavors of fermions here, it's the number of flavors times E squared T squared. Yeah? Sorry, it's 1/3. 1/3. Yeah, so it's similar as in the scalar case. There we had a T squared, and there we had a lambda, and the lambda corresponds to E squared. And this is just here from basically counting degrees of freedom and so on. Okay, now what is this? Well, this is not the end. This is not just the thermal mass, because we know we have this funny structure appearing here. And let me write it like this. So this is a term which is indeed a constant, but only for the 0, 0 component. And then we have something proportional to the k naught. And then there's an integral over the directions of p. It's convenient to write it so that this integral without anything would be 1. And here we have v mu over v dot k. So this here is this expression, which we saw appears in the denominator. So I have introduced this object v mu with 4 components. So far I had only the velocity here. So this is 1, and in the 0 component, and in the spatial component, it's the velocity of the particle in the loop. Yeah, and then we see that we can write this expression here just as a scalar product of v and the vector k. So we get this, and here we have this we get basically from this part here. Okay, so this is the result, which is in the case that the k naught. So let's try to see a bit of the structure here, how it looks like, or maybe simplify. So for, let's see, if we do thermodynamics, then we have, when we have soft momenta, the k naught has to be 0, because that's the only way for k naught to be small. So for k naught equal to 0, then this looks just like a mass term. Yeah? So this gives a mass to the 0 component of the vector potential, for vector potential. And remember, this is the 0 component of the vector potential is the scalar potential. And if we have 0 frequency, then there is no dynamics, everything is static. So this, the mass is actually the dBi mass. This then gives a mass to this static scalar potential. And what does the scalar potential do? It gives you, for example, the Coulomb field of an electric charge. And if it has a mass, it means that at large distances the potential or the field falls off exponentially, meaning that the plasma in which this, so we have all these charged particles flying around and we put a charge, and what the plasma does, it screens the charge of the charge that the field of this charge that you have put in. So this gives you so-called dBi screening of a static charge. But the spatial A is not screened. In particular, magnetic field, which you get entirely from the spatial part here, is they are not screened, so there's no magnetic screening. Now, if we go to non-zero k, then we get something which looks quite different. And then you see also the spatial components of the pi mu nu are non-zero. So this was k not equal to 0. So both spatial and temporal components of A get screened. Which is what people refer to as dynamical screening. Okay, so one could say, of course, a lot more about this expression. You see when you have this thing here in the denominator. Now, if, for example, suppose the vector k is time-like, meaning that this here, k naught is bigger than the length of this vector here, then this never vanishes, because this is a unit vector, and that is always greater than this thing here. So at time-like momenta, this thing is real, and what it does basically is it gives something like a mass to the photons. So it's like changes the dispersion relation. Now, if k is space-like, that means that this here, k naught, the absolute value of k naught is less than the absolute value of k, then you can have poles. Now, remember what we need. We need to approach the real k naught axis from above and below and take the difference to get, for example, here the production rate. So we take the discontinuity, and this then gives you an imaginary part. So for space-like momenta, the Hardt-Thermal loop here has an imaginary part which describes damping of your fields. And that's called Landau damping. Okay, but now, so now we see what is the structure of Hardt-Thermal loops. And now comes the second part of what I want to tell you today, is how we can understand the physics behind that. Because when suppose you would do the similar calculation in QCD. So there you would have here you would have a gluon field. And again, you have fermions, but you also have gluons, because you have gluon self-interactions. So you have a lot more diagrams, and you can have different species in the loop. They could be bosons, fermions, gluons and quarks. And the funny thing is, yes?
Dumping? What is the lambda damping? Can you explain once?
Okay, I cannot go into the details. What I'm saying is when you have space like K, yeah, okay, then the pi mu nu gets an imaginary part. If you resum the pi mu nu into the propagator, it would be like a thermal mass if it was real, but now, so to say, very roughly speaking, the mass gets also an imaginary part. So you have an imaginary part downstairs in the propagator which describes damping. Yeah? Yes?
So even for the k equal to 0 part, you mentioned that there's a Debye mass, so that could also lead to fields dropping off at large distances, if I got it correctly.
I mean, yeah, everything is proportional to the Debye mass, but it's really just gives you the size of the total thing.
So
And
does
the
it
K
also?
is,
Yeah. So I mean, my question was, you mentioned that the plasma screens the field of the charge, so at large distances it falls off. So is there also like some kind of exponential damping factor there?
Yes. I mean, there's always the real part which comes with the m Debye, and that would give you. Well, it depends. Okay, I mean, one has to be a bit careful. You see, this is a tensor, second rank tensor, and this has, you can decompose it into two components. One comes, roughly speaking, corresponds to electric modes, and one corresponds to magnetic modes. Now, if you look at the part which has only the magnetic modes, then this will be screened as long as the K naught is not too small. If the K naught becomes too small, then it will not be screened. Does this answer?
So even if Debye mass is non-zero, I mean, k naught equal to 0 has nothing to do with Debye mass. Is that true?
No.
Or no.
No.
So MD also should go to 0 when k naught goes to 0. Sorry, I think I'm a bit
Sorry,
confused.
what else goes to 0?
So I'm just saying that the k naught equal to 0, does that imply the Debye mass is 0?
No. I mean, the K naught, if the K naught is, you mean this here?
Yes.
Well, then this term goes away,
Yeah.
and then you have only the Debye mass. This is still here, but this affects only the A naught, and not the other fields.
Okay, that will not screen the vector part of the potential. Okay. Okay, got it. Thank you.
Okay. Now, let's try to, so yeah, what I was saying is if you do the same type of computation in QCD, where you have like quarks and gluons, you get exactly the same expression here. The only difference is that the Debye mass has now different values because it gets contributions from all the hard fields in the loop. But this structure is precisely the same. And this means that there must be some very general physics behind this. So it doesn't really depend much on the details of the theory. And this is the case. And I want to show you this now. I do this in two steps. So first I kind of rewrite our process of resumming. Yeah, let's think a second again about what we do when we resum this hard thermal loop into the propagator. So resummation, we can remember we did this very explicitly for the scalar field case. So for scalars we had this propagator, and then we had the one hard thermal loop, and we have a second one, and so on. And we said we sum all these terms and get a new propagator, and then we said that the resummation can be represented by replacing the tree-level mass of the scalar field here, m squared by m squared plus the thermal mass squared, which is basically just this blob here. Yeah? Or now you can formally state it like this. So the propagator can then be obtained from some effective action Remember the propagator, to compute the propagator, we only need the free action, meaning we don't have to include interactions. So this is what I denoted by S naught. Now we use the effective action here without further interactions, which is the tree level action, and then the new term, which represents the mass term, which is integral d for x, and then thermal mass squared times phi squared. Yeah, this is just a term in the Lagrangian corresponding to a mass, and we can do the resummation by not using just the usual action, but the usual action plus this thermal mass term. Okay. Now let's do the same. Try to do the same thing here. Now we have, instead of the scalar field, we have a electromagnetic field. So now we are dealing with the electromagnetic field, where the free action is -1/4 integral d for x, and then f mu nu, f mu nu. So this is the electromagnetic field strength tensor, and this gives us, well, we still have to fix the gauge, whatnot, but this gives us the photon propagator. And now, how do we represent the hard thermal loop? Well, basically the same structure. I mean, we put in two fields, so in this case, two vector potentials, and then here the hard thermal loop. The difference or the difficulty is, of course, that this is not simply a constant like it was in the scalar case, but it's a function of k, or if you go back into position space, it's a function of x and x prime, where x and x prime are the locations of the fields. So including the hard thermal loop in S naught effective looks like this. So S naught effective is S naught, and then -1/2. So far, so good. But we have, to get to this expression, we have to Fourier transform this, go into position space, and then plug this into this expression, integral d for x, d for x prime, and then we have, say, a mu of x, and then the Fourier transform of that object, pi mu nu of x minus x prime, and then a mu of x prime. Yeah, if that was a constant, this would just be a delta function, which would eat up one integration, and we would simply have a mass term like here. But if due to this term here, I mean, if it was only this one, we could do that. But this term here spoils that. I mean, the Fourier transform isn't a delta function in position space. So this makes this object here non-local. So it's non-zero even if x unequal to x prime. So this is a non-local contribution here to the action. Okay, yeah, this looks complicated.
Is it gauge invariant?
Yes. I didn't show you. It is, yes. That's actually not, I mean, the reason is that I wrote earlier that this is a two-point function of electromagnetic current. Electromagnetic current is conserved, and this makes sure that this is gauge invariant. That's, of course, a good point. This expression here is gauge invariant. Very good, thanks. Yeah, and now let's see. So what do we do with this? Now I imagine that instead of quantum field theory, we are dealing with classical fields. So we are dealing with classical electromagnetic field. And now then you can ask what would be the equation of motion for this classical field if you have not just the usual action but also this additional term. And of course you can here take this expression and vary, and then you get, so now we treating a mu as a classical field. Field one, we obtain it's not an effective, gives the equation of motion. So by varying this part here, we get the usual d nu f nu mu. And by varying this part here, we get, well, we basically take away one of the a's. We can take away both, so 1/2 is cancelled, and what is left is still a single integral. So it's an integral d4 x prime, and then pi, say, mu nu of x minus x prime times a nu of x prime. Let me check the sign. Yes. Okay, so this looks like Maxwell's equations here, and if remember in Maxwell's equations on the right hand side we have a 4-vector current. So we have Maxwell says d nu f nu mu is a current. So we can think of this as a Maxwell's equation which has a current J mu so star looks like Maxwell's equation with a non-local current. So there's a current which depends on the vector potential also, and it's non-local. So you have a current which at some point x that also depends on the value of the vector potential at all other points. Well, not all, but on many other points. where the current, where J mu is a non-local functional of A. Yeah, this looks very strange and complicated, but now I show you, well, I rederive the current here by looking at classical plasma physics. So I completely go away from quantum field theory and consider J mu from classical plasma physics. Okay, what is plasma physics? Well, in plasma physics, you have particles which are charged, and they are unbounded. They fly around freely, and they interact with the electromagnetic field. Yeah? So we have charged particles, and I have an index A, which numbers their species interacting with electromagnetic field. Okay. Now the particles, they are described by the phase space density say, well, before we had the Fermi-Dirac or Bose-Einstein, now it's some general non-equilibrium distribution, which depends on time and space and on the momenta P. So if it's the density of number of particles in space-time volume, d3x, d3p. Okay, now we have we want to see how these evolve in time. And remember, if we don't have collisions or so, then Liouville's theorem applies, which says that if you have a trajectory in your phase space, then the phase space density along this trajectory is constant. Yeah? So assume that we have no collisions. Then Liouville's theorem says that Fa is constant along phase space trajectory. Yeah, so we get a differential equation, the total time derivative of Fa. Why does it change in time? It changes in time because of explicit time dependence. Then it changes because the particles move. So it's times the velocity of the particles x dot. And also it changes because the momenta can change, because we have this electromagnetic field, so there's a force. So we get a term Fa with respect to p times p dot. And the sum of all these is 0. I'm sorry. Yeah, right. Yeah. Okay. Now the x dot is already, well, I already said it's the velocity of our particles, which again we assume massless particles. So it's p over the length of p, so mass equal to 0. And this corresponds to neglecting the mass here in the hard thermal loop, by the way. Now, what is the p dot? It is the Lorentz force acting on the particles, so it's the charge, and then you have field strength m. We can write it like this with v nu. Yeah, it has the zero component is here, it's just 1, then it's the electric field times q, and the spatial components, this gives you v cross the magnetic field. So that is the equation of motion for the momentum, and then we finally need the electric current in terms of the phase space density. So J mu is equal to of x is equal to, well, now we sum over all the species in the plasma QA and then integrate over the momenta P of the phase space density Fa of x and p. And then we need the, so to say for the current, spatial current, we need the velocity. So there's a v mu here. Okay, so we have these equations here, and this here together with this is the so-called Vlasov equations. So the set of equations is called Vlasov equations. Okay, now we want to simplify them.
I have a question. Yeah, this is like all classical analysis, right?
Absolutely.
So there, when you write m equals to 0, that is confusing me. Then, I mean, it should be the speed of light, right? I mean,
Yes.
is massless particle.
Yes.
So that v that you define, I'm not sure. I mean, also that is like dimensionally incorrect, right? X is position, right?
Yes.
So you write x equals v equals p by mod p is dimension. Yeah, sorry, it's x dot, sorry, yeah. So, which is the dimension of velocity. So, but p by mod of p is dimensionless, right? This p by mod of p.
This, yes.
Yes, so that is dimensionless, right? The right hand side.
Yeah, it's dimensionless. So it's the speed of, yeah. It's I put, yes.
You c is equal to 1.
Yes. Yeah. C is equal to 1 always.
Okay.
Sorry,
Okay,
I said this in a.
Okay,
Yeah.
thank you.
Yeah. C. So C and h bar and Boltzmann constant are all equal to 1.
Okay.
Yeah.
Thank you.
Okay. Now we want to solve the Vlasov equations in the simple case that we are almost in thermal equilibrium. So we consider. So what is thermal equilibrium? Then we have our phase space density equals the equilibrium density, which I denote by F bar. So this could be either Bose-Einstein or family-Ruck. Yeah? And this is equilibrium distribution. Oh, so this is F Bose or F Fermi. And furthermore, if in thermal equilibrium, you should have no fields, because they would drive the F away from equilibrium, so we take F mu nu equal to 0. Now, now we consider small fluctuations around equilibrium. Which is that I write Fa is Fa equilibrium plus some delta Fa, and F mu nu non-zero. But I will linearize in everything which is has more than 2 powers of this, or mixed F delta F times field strength. Okay, so linearize our Vlasov equations. So let's see, what do we have? We have this term here with the Lorentz force that we can simplify. So we have dFA dP times P dot. What is that? Now the P dot is proportional to the field. So the field is a small quantity. So it means here I can put in the equilibrium distribution. So that I replace by dF A equilibrium dP times P dot, which is, well, this only depends on the modulus of P, so this is, let me just call this Fa prime, it's the derivative with respect to energy of A, and then dP, d modulus P with respect to P is, so d modulus P dP. This again gives us the velocity V. And yeah, then let's leave this there as it is. So here we have Fa bar prime times velocity. And now I put in what is the Lorentz force. I get a Qa, and then F m nu V nu. And this is contracted with a V from here. Okay? Now this is an antisymmetric tensor, so that if I have here Vm and I have here Vn, I have something symmetric, and this is antisymmetric, so this gives 0. And the only contribution comes from when this new index nu is 0. Yeah? If nu is a spatial index, this gives 0 here, and I can write this as Fa bar prime times, well, I can pull out the Q, Qa times Fa bar prime times Vm times Fm0. Now Fm0 is nothing but the electric field. So this expression is equal to the charge of the particle times the derivative of equilibrium distribution times V dot, the electric field. Okay, so then we can plug this here. We don't, yeah, here at this place we have to take the here the equilibrium distribution gives 0, so this will contain the delta F. And if we collect all this, we get the linearized Vlasov equation, which is Well, the first two terms here, the time derivative and this flow term with the velocity, I can nicely write as v mu, d mu, and I have the delta Fa. And I put the Lorentz force term on the other side, then I get a minus sign here. It's minus Qa times Fa bar prime times v dot E. Okay, now this type of equation it's a linear differential equation, and we can solve it by Fourier transformation. We write this as integral. We integrate this over d for x e to the I kx. And then both sides of the equation. Why is there a plus I? Is that correct? This is minus signs. Yes, of course. It's a plus. I get the, I integrate here by parts. So then this gives me, the first term gives me a minus I. I was confused about the sign minus I. And then here, the derivative turns into the k mu. So I get v dot k times delta f a of k. That's the left-hand side. And on the right-hand side, we have minus qa f a bar prime v dot e of k. Okay? And the current, let's write the current. Well, we can solve this. I mean, now it's an algebraic equation, and we can write, to get the solution, Fa of k equals to minus Qa Fa bar prime, and then plus I over v dot k times v dot E. Check the sign. Yeah, it has a minus, and then we can use this for the current. The current is 0 in equilibrium because we have equal number of positively and negatively charged particles, so that if you plug the equilibrium distribution here into this expression, you get 0, and the only contribution comes from the delta Fa. So the current would be then J mu of k equals to minus sum over A. Now we have 2 times the charge Qa squared F A bar prime, and then, F A bar prime, and then the delta F. No, that's my delta F, sorry. This is minus Q times delta F times V. So I have integral over momentum, and my delta F here is Fa bar prime I over V dot K, and then V mu V dot E. Yeah, that is the current I get. Okay, now we have a integral again over momentum space, and we see the same structure as we saw in the field theory calculation, that the integral here over the modulus of p and the direction, they factorize. I mean, this depends on the modulus of p, but this does not. This only depends on the direction. So we can do the integral here, and this integral here can be done well, let me write it like the whole here. Oops. So this, okay, I write this as a do the factorization of the integrals. I have sum over qa squared, and then I integrate over the modulus of p. So I have integral from 0 to infinity dp p squared, and then the derivative of fa bar with respect to p. Yeah, this is the f prime. And then I have the integral over g omega of the rest here. So it's I over v dot k times v mu v dot e. Yeah, so this is one integral, which I can do because I know the equilibrium distribution, and what is left is here the integral over the direction of p. Now, here I can integrate by parts, and so this here gives us -2. If I integrate by parts, I get the derivative of this term. I get a minus sign, -2 times integral dp p fa equilibrium. And yeah, so that we can write as -2 integral 0 to infinity dp. Okay, let me write this in the form of the original integral. So put here p squared, so I have to divide by p here, fa bar. And then I have so here,
Because you had a minus sign already on the outside.
where's the minus sign? I'm looking for a so I think the sign is okay. Let me see. So now we should specialize. Now we have to do this integral here, so we have to know what the equilibrium distribution is now. And for simplicity, we specialize to the case now that we have electrodynamics just with electrons. Now consider only one species of fermions. So we have f a bar is the Fermi-Dirac distribution, and then the integral d3p over 2 pi cubed, which is this integral here of f, is Fermi-Dirac over p is equal to t squared over 24. And actually, I forgot something here, which is 1 over 2 pi cubed. Sorry. Yeah, that we have to include, and this is why this is also included here. So here we get this t squared over 24, and then we only have this expression here with the integral over omega left. So we have j mu, or we can already do the sum over the q squareds for our case. Now if we have qa squared, in our case if we have electrons and positrons, we get factor 2, so e plus e minus. Then we have spin 1/2, so it gives another factor 2. We can have 2 spin orientations, spin 1/2, and then the charge of each of the particles is e or minus e, so we get e squared. So 4 times e squared. Okay, now let's try to put everything together and compute the current. J mu equals to 4e squared from here. Then we also have a minus sign from the front. Then we have another minus sign here. This is minus 2. Then we have the integral over momentum, which was t squared over 24. And okay, just pause for a second and look at these factors here. So we have minus minus is plus. 4 times 2 is 8. 8 over 24 is 1/3. And remember from some time ago, we had that this is the Debye mass squared, right? So you have 1/3. We have only one flavor, so this is equal to 1. And this prefactor is precisely the Debye mass squared that appears here. And now comes the angular integral. Which is left, so d omega over 4 pi, and with, I have the I over v dot k from here, Then what else? I have a v mu, and then this here, which again I write in terms of the field strength tensor. So I have minus, can write this as minus b mu 0 like this. So there's a, remember Fn0 is the plus the electric field, but here the index of the nu is downstairs, and with my metric convention that is minus in the spatial component, so this gives us plus v dot e. Okay, can I have 5 minutes? Yeah, okay. Then I will be able to finish. So now we should still look at this. Okay, now what can we do about that term? We have minus v nu f nu mu f nu 0, sorry. We write the field strength in terms of the vector potential, and remember we have Fourier transformed, so the derivatives now correspond to minus ik. Okay, so this is minus v nu. Then I have a minus I here from the, and I have a k nu times a naught minus k naught a nu. Yeah, this is minus, this here is the electric field in Fourier transformed. And now we see here v nu, k nu is a v dot k, which appears here also. So I have here minus I times v dot k, and then minus k naught v nu times a nu. So that we should insert into this expression, into the integral. And then this term here will cancel this denominator here, so that the only dependence on the direction of velocity sits in this term here. So we integrate over the direction of this object. So the zero component is 1. So the zero component integrated gives 1. The spatial components give 0 because we integrate the vector over all directions, which add up to 0. So what we get for the current is J mu equals to d by mass times integral d omega, or we can already make this explicit. We have tried to get the signs right. Minus I times plus I gives plus 1. Then we have the a delta. Oh, sorry, I forgot the A naught here. Say A naught. And this one I forgot. So I want to pull out an A nu. A nu. So the first term has a delta nu naught, because there's only the A naught appearing. And here I have K naught times B. No, sorry. There's no delta K naught. There's a, I can, sorry. Did I write this here? No, this is correct. And I can have here right integral d omega over 4 pi and just plug in the terms I have. Integral and then v mu over v dot k. And the first term is v dot k a naught. And the second term is k naught v dot a. V nu a nu. As I said here, this cancels. This gives only something if actually I have a minus sign here, right? Minus m squared d by. And then this is minus d by mass squared. And the first term gives only something if mu is equal to 0. And I have here a delta A naught only, so that if I pull out an A naught, I knew here, then this gives me the A naught. And here we have left still the integral d omega over 4 pi times v mu, and then the v nu over v dot k. Okay, and then you see this is precisely of the form hard thermal loop pi mu nu times A. I missed. Sorry, where are you?
Yes, in the second expression.
Here? I missed, in this expression, I missed what? D by mass?
Second line, sorry, second line.
The second line.
Second line,
Second line, second line.
yes. K naught with the,
Ah, sorry, yeah. Wait, so there's a V, V. There's a V nu here. Sorry, yes, thanks. No, this is
Delta nu 0.
right. I can write this as a delta nu 0. Right. Yeah.
Yes.
Now I got it.
And also this 4 pi factor, d omega by 4 pi factor. Where is this 4 pi below d omega is coming from?
D omega, this is 1. I mean, if I have nothing here.
Okay.
So that's why the 4 pi is there. Okay, so
Okay.
the message is that the J mu so the bottom line is that from the classical plasma physics we obtain that the current is equal to pi a nu of k times the a nu of k. Yeah? So meaning hard thermal loops in a gauge theory are described by classical particles interacting with classical field. Yeah, and that's why, so the only thing which matters is really that you have massless particles with charges and they interact with the field in a, all in the same way. And the difference between the species just enters the Debye mass. I mean, you have to count the degrees of freedom and the charges and all that and put them together. And you know, this is kind of interesting because suppose we had only gluons. So this was pure Yang-Mills theory, and we would play this game. So we would compute the hard thermal loop in pure Yang-Mills theory. So with only gluons, we would get this expression. But then I told you, okay, but this is the same as having classical fields interacting with classical particles. How can that be? I mean, all of a sudden you have classical fields and classical particles. And remember the hard thermal loop, the particles in the loop, they were momenta of order t, and they correspond to the particles. Whereas the soft fields for which we did the resummation, they correspond to the classical fields. So one and the same quantum field has two completely different classical descriptions in this picture. I mean, the high momentum fields, the hard fields, they are represented by classical particles moving on classical trajectories, and the low momentum fields are described by classical fields which give the forces on the high momentum particles. So you get kind of two different limits of quantum field theory only for one type of quantum fields, just depending on momentum. Okay, that's the end. Here?
No, yeah. There's, in JMU, just before your boxed equation, the second equation should have a k naught. No, on the right-hand side.
Here?
No. This is the boxed equation of JMU.
Sorry, but this
The last boxed equation.
the last box. Oh,
Yeah,
this
just
one.
above that. Yeah, just the equation before the box should have a k naught over there. Delta mu naught, delta nu naught minus k naught times d omega integral.
Sorry, of
Yeah.
course. Yeah. Sorry, no, I forgot this.
So I don't,
Yeah, no, you're right. This is this K, the K naught here. Yeah, that comes from
that's the
from
K
here.
naught, yeah.
Exactly,
There's a
yeah.
K naught
Sure,
there.
very good.
Yeah, I have a question now actually about the classical field. So you have a classical field, but you have actually taken the quantum description of the statistics because you've taken the Fermi distribution. So I'm not able to quite understand why you do that.
You mean for, sorry, what do
You've taken classical fields, right? So all your fields are classical.
yes?
But when you take your statistics, you've taken the Fermi distribution.
Not
So-
all my field, but this is for the particles.
So the particles are quantum, but the fields are classical, is it?
Okay, this is a bit, you touched a point where, where things were not quite classical. So what I said was ignoring this fact. That is correct. You should, I mean, you have classical particles in the sense that they follow classical equations of motion, which are determined by the Lorentz force and Liouville's theory, okay? In that sense, that is a completely classical description, but you're right. At the moment when I use the Fermi-Dirac distribution, I put in something quantum which is not contained in classical plasma physics. That is, you're right. So in that sense, it's not completely classical.
Okay, I see.
And but okay, I mean, after all, it's we started from quantum field theory. We got this expression where without really from first principles, and there we know we have to use Fermi-Dirac. But still, I think this is an important insight that you know what happens. I mean, you get all of a sudden you get, instead of a mass term, you get this non-local expression, yeah, and you want to understand what is behind this because it's so universal. It must be something simple, and this is a simple picture.
No, absolutely. Thank you.